Before I get started, there's actually an extremely important order of business. Where is the gentleman from the party last night who said he could decide the truth or falsehood of any mathematical statement? Not here?
I think he just wandered in off the street.
I see.
But 5 minutes.
You? No. Are you still offering oracular services? Can still give me some light? Okay. Do you want to come up?
How useful is a black box, though?
Oh, very useful, I think. All right, good. So I'd like to channel Feynman's spirit. So tell me something. Is there a problem such that for every algorithm that solves it, there is also an exponentially faster algorithm?
Yes.
That's correct. Is there a theorem that can only be proved by assuming its provability is an axiom?
No.
That's correct. Are there two perfect powers that differ by one other than 8 and 9?
Sorry?
Are there two perfect powers other than 8 and 9 that differ by only one?
No.
That's correct. Is every odd number greater than 1 writable as the sum of a prime number and a power of 2? No, that's wrong. 127 is a counterexample, but that was a very good showing. All right.
Why weren't you doubling the money for each?
Well, I'm not the one who's supposed to be offering prizes here. All right. I'll tell you what, email me. You can have a free copy of my book. All right. What? You'd rather have the money?
He already has one, but
Oh, he already has one? Oh, all right. Well, then I can get you a beer. Okay, that's sort of like the inverse of the book, I guess. Maybe the same thing, actually. Okay, maybe the book is self-inverse. Okay, so all right. Last time we saw sort of some of the basic actors on the stage. There's complexity classes, what you can do deterministically with a randomized algorithm and with a quantum algorithm. It's P, BPP, and BQP. And we saw sort of how these things fit together. Particular, the Shor's great result was that, BQP contains some of the problems in NP, like factoring and discrete log that we don't know or believe to be in P. Well, believe depends who you ask. On the other hand, we certainly don't know if the BQP contains the NP complete problems. In fact, I'm not sure if I mentioned this, but there are many other problems in NP, even besides the NP complete ones that we don't know to be in BQP. So Stephen mentioned the problem of graph isomorphism, which as far as we know is sort of somewhere up here. We have very strong reasons why it shouldn't be NP complete, but no one has discovered a quantum algorithm for it either, and they've been trying for 20 years. Okay, so so BQP sort of seems to fit in this sort of odd way. And of course, BQP might also have some things that are not even in NP, but this we're not quite sure about. And partly it depends what you even mean by a computational problem. If you're, as we'll see later, languages, we don't have any good examples here, but search problems and sampling problems, we do have very good examples. Okay, so Okay, so the question is, my starting point for all of this was the extended church Turing thesis, the ECT, this amazing claim, bridging computation and physics. And question is, isn't Shor's algorithm sort of already, the sword that has slain the ECT? Okay, if you believe factoring is classically hard, then it shows that there is some physical system, consistent with the laws of physics that we know, that does something faster than the fastest classical simulation of it. And that's a counterexample. Okay, well, that is indeed part of why Shor's algorithm was such a great discovery, because it did create this tension between quantum mechanics and the ECT. I mean, to me, that's more exciting than being able to read people's email. Which in any case, there are easier ways to do that, as we've learned over the last few months, I guess. So, but there are a few issues that we might worry about if our goal is to sort of overthrow the empirically the extended church Turing thesis. The first issue is simply that factoring, as we discussed, is an extremely special problem. It has all sorts of sort of special structure, of course, is what Shor exploited, but it probably doesn't capture even the full power of what a quantum computer can do, right? It's a very specialized thing, and some number theorists, going on record saying they think that it's probably in P, that there is a classical algorithm for it, and we just haven't discovered it yet. So, so what we would really like is to base our belief that quantum mechanics violates the ECT on something which is sort of more secure than factoring, something that we have really stronger reasons to believe is classically hard, right? The way I like to put it is that if factoring had a fast classical algorithm, that would merely collapse, the world's digital economy. It wouldn't collapse the polynomial hierarchy or anything like that. Okay, so, it could be right. It could be in P without any, particularly bad, theoretical consequences, right? It's like we don't really. I mean. So the question, and of course that's a problem for cryptography too. It would be great if we could base public key cryptography on an NP complete problem, for example. People have been thinking about that for 40 years, but it's still not known whether one can do that. Okay. Yeah.
I'm just curious. I mean, isn't the ECT already just killed by the statement that it's generically hard to simulate quantum mechanical systems on classical computers? Just you have some spin system, yeah. You want to know the result of a measurement.
If you believe that statement, yes. The question is, what are the grounds for believing that statement?
Oh,
that's exactly what we're talking about. Yeah.
But I thought, don't you even just know that simulating a generic spin system with a local Hamiltonian is NP complete?
Well, first of all, okay, if we're talking about ground states, then we're talking about problems where nature itself doesn't necessarily find the solution, right? Nature itself may get stuck in metastable states,
no, I don't
right?
Do that. I want to start in some state and then evolve from
Right. Okay, well then, all of our beliefs are only as secure as our belief that, BQP is larger than P, essentially, right? I mean, so this is exactly the question that we're asking, right? There's a clever classical simulation that no one has thought of. How do you rule it out? On what grounds do you say that it could never exist? Okay, that's exactly what we're talking about.
Well, in general, can't you just not do better than just writing out this, like you said, the
No one knows that. No one knows that. That's again and again in computer science, right? I mean, in the early days, right? People said, for example, for multiplying two matrices, right? It's obvious that you need n cubed time, right? It's because what else are you going to do than multiply each row by each column, right? But it was obvious, but it was wrong. You can do better, right? And so this is why this is why people became more rigorous, right? It's not just because they're like masochists who enjoy rigor for its own sake, right? It's because when you just use intuition to say, well, this is obviously the best thing you can do, then again and again people have been wrong who've said such things.
Shor's algorithm
Yeah.
is a very simple quantum system.
Yeah.
I predict a
It's a very simple one. It depends, I guess, what definition of simple we're using. I mean, it's complicated enough that no one has been able to exhibit it yet on any large number of
parts. That's just because experimentalists don't know what they're doing. But in terms of, you could describe it in a page.
Yeah.
But I mean, I could think of lots of things that you can't describe.
But okay, but the fact that it takes you many pages to describe the thing says nothing about its computational complexity, right? That's right. The number of pages is just like a constant overhead, right? It's just, I mean that may mean that you need a longer program to simulate the thing, but it doesn't say anything about the running time of the program. Okay. And look, to make it more concrete, right? We do have fast algorithms for simulating a huge number of the sorts of quantum systems that arise in nature, right? We have density functional theory. We have, the MRG, right? We have, the matrix product state methods. We have all these methods, and, against the intuition that, it's obviously hard to simulate, right? There's other physicists who have the intuition, it's obviously easy to simulate because.
That's all Euclidean, though. That's different from doing real-time evolution and then, projecting on.
Okay, but then, you have to find examples where it's hard, right? I've talked to people who had the intuition that, quantum computers should be easy to simulate because we have these methods that, always seem to work for simulating quantum physics. Now, I don't think that's true. The question is, what grounds can we give for that not being true? Okay, so, now a second point is that, as we saw, factoring is in NP, even in NP intersect co-NP. So certainly Shor's algorithm is not going to give us any evidence that BQP is, extends out of here or, outside the whole polynomial hierarchy or anything like that. We might be more ambitious and we might want some evidence for that. Okay, and then the third, and most obvious issue, right, is that Shor's algorithm is just, very hard to implement. In fact, implementing it doesn't seem that much easier, maybe a little bit, but not that much easier than simply building a universal quantum computer. Okay, and, this is, we hope it will eventually be possible, but we're not there yet. Okay, so again, what we'd really like would be to be able to look at like quantum systems that are found in nature, right? Or at least in the lab, sort of more naturally occurring ones, and say, look, these systems too are hard to simulate by a classical computer, sort of like Daniel was suggesting, but we would like to really give an argument and say, if we had a fast classical simulation for these things, then it would have a bad consequence, for something else. Then it would mean that we can, really, collapse the, hierarchy of complexity classes in some dramatic and unlikely way. Okay, and that's the kind of thing that we want in order to convince us that, that the difficulty is really inherent. And it's not just a matter of, we didn't think enough about, how to find the algorithm. Okay, we want to do better than that. Okay, so as it happens, we have a proposal that addresses all three of these issues. Coincidentally, so that's what I'm going to sort of talk about for the remainder of this lecture and the next one. So I'm going to talk about optical quantum computing, in particular a proposal called Boson Sampling, which Alex Arkhipov and I described about 4 years ago. This is just sort of one particular proposal for trying to heighten the tension between quantum mechanics and the extended Church-Turing thesis. There can be, and in fact there are, other proposals. There are a lot of different ideas. I think Steve mentioned some of them for, physical architectures that would give you some of quantum computation, but not necessarily all of it. Okay, there's something called the IQP model. There's something called the one clean qubit model. You can have bounded depth quantum circuits. Okay, those were studied in actually a decade ago in a paper by Terhall and DiVincenzo that actually anticipated what we're going to do with boson sampling and in several ways. So there have been a lot of ideas floating around about how you might more easily than by building a universal quantum computer, you might be able to do something which we can really give some decent evidence is classically hard. Something that we think is outside of BPP. And here I should say from the outset that we're going to try to achieve all three of the, we're going to try to fix all three of these issues. We're going to give up on the goal of doing anything practically useful. Okay, we don't care about that. We're merely trying to overthrow the extended Church-Turing thesis. Okay, and prove that nature does have this computational capacity, which seems like sort of an obvious first step if your goal is to someday do something useful with a quantum computer. Okay, so so optical quantum computing is just one particular idea where we've thought through a lot of the issues, and where sort of actually complexity theory and actual experiments that people are able to do today sort of interact with each other and come together in a way that I think is kind of remarkable. I think I never encountered anything like it before in my career. So okay, so what is the quantum optical computing model, or the linear optical model? So here, I'm going to start sort of discussing things that actually, are more familiar to many of you than they are to me. But the way that I'm going to describe them might be a little bit non-standard. So let me just go through this. You can see that I sort of pre-computed this stuff on the board. Save some time, but okay. But so quantum optics is going to be like a type of quantum computation, but which is not based on qubits at all. Okay, it's not based on a Hilbert space that has a tensor product decomposition. Instead, it's going to be based on these hypothetical entities that we're going to define, which we'll call bosons. Okay, and and as a very happy coincidence, it will turn out that the physical world will also provide these bosons. One good example is photons. Okay, so we're going to imagine that we have a computer with n identical non-interacting, let's say, photons. Right? Everything I'm going to describe, you could also do with Higgs bosons, but it's a little harder to arrange. Okay, so let's say you've got n identical non-interacting photons. Right, they're going to enter in, let's say, on the left side of your optical network. They're never going to be created or destroyed. So the photon number is going to be conserved throughout, and each one is going to be in one of m modes. Okay, mode being just a place where it could be, or I don't really care what kind of mode either. If they have polarization, that's fine. That's just an additional mode as far as I'm concerned. Okay, and we'll be working in what I learned recently is called the dilute limit, which means that the number of modes will be greater than the number of photons. Okay, sometimes we'll want it to be quadratically greater. For now, I'll just say it's it's at least somewhat greater. Okay, so most of the modes are unoccupied. Okay, so what? How do we describe such a system? Well, I'll work in the Fock basis. So our basis states just consist of lists of non-negative integers. Okay, so say like S1 up to Sm. Okay, where Si tells you how many photons there are in the ith mode. Okay, so these are just not non-negative integers summing up to n. Okay, and so just a little notation, I'll let phi mn be the set of all possible such basis states. So all possible lists of how many photons there are, in each of the modes. So, how many such lists are there? Well, so that I put this on the homework. This is a little, combinatorics exercise. You can prove that the answer is this. It's m plus n minus 1, choose n. Okay, and so, so if you've got, let's say, n photons and n squared modes or so, then you do have exponentially many basis states. Okay, and this is important. We're going to need exponentiality somewhere if we're to hope for a computational speedup. Okay, and I'll sometimes call this capital M. Okay, so how do our photons start out? Well, they're going to start out in what I'll call the standard initial state, which I'll call I. Okay, and this just means that we've got one photon in each of the first n modes. Okay, and the remaining m minus n modes are unoccupied. So it looks like this. Okay. So I'll just for simplicity, I'll usually take this to be our initial state. Okay. So then this is quantum mechanics. So of course, the general state of our optical computer will be a superposition over all of these different basis states. So it'll be something that looks like this. Okay, where for some normalized set of amplitudes. Okay. Okay, but now what operations can we apply to these states, right? And how does a unitary transformation affect these guys? Okay. Here it's easiest to start with just the special case n equals 1. So let's say there's just one photon. Then of course our state will just be like a one photon in a superposition over each of the m modes. It'll just look like that. Okay, and now we can take such a state and we can apply whatever m by m mode mixing unitary transformation we would like in principle to this photon. What does such a transformation do? Well, it does the obvious thing, the only thing it could do. It maps psi to u psi. Okay, so that's just how classical light behaves. All right, so far you could say there's nothing really too magical here. Okay, but already here there's an interesting question to address, which is, suppose someone described to us an arbitrary m by m unitary transformation u. How would we implement it? Could we implement it? Okay, just like in standard quantum computing, we can't just assume that we can apply any unitary whatsoever instantaneously. We have to build up more complicated unitaries out of simpler ones, which we call gates. Okay, so in the world of optics, the analog of gates are called beam splitters, and there's another one called phase shifters. These are just the analog of like 1 and 2 qubit unitaries, as Steve described in the qubit model. Okay, and but now a big difference is that these are now going to act on only 1 or 2 modes at a time, and as the identity on the remaining modes. Okay, and and it's really, instead of taking a direct product, we're going to be taking a direct sum. Okay, so a little bit more formally, a beam splitter looks like this. It's an m by m unitary transformation, which acts as the identity except on 2 modes. Okay, where it does some little 2 by 2 unitary transformation. Okay, let's say of our choice. Sometimes people also assume that it has to have determinant -1. Okay, whatever. A phase shifter is just an m by m unitary transformation that looks like this. Okay, it's the identity except on 1 mode where it it applies a phase. Okay, so now a question already arises, which is it possible to build up any possible m by m unitary transformation by multiplying together a bunch of these guys? Okay, Oracle, what do you think? Yes. All right. All right, so there's a simple theorem. I think I even gave it on the homework to try to prove it for yourself, due to Reck et al. From 1994. Okay, which says that in fact you can implement any m by m unitary transformation using a network consisting of only O of m, order of m squared beam splitters and phase shifters. Okay, and furthermore, if someone tells you the unitary, then you can find that decomposition efficiently. Okay, it's easy to figure out how to do this. And the proof is really just to sort of basically it's like Gaussian elimination, right? It's it's sort of a fun exercise, and because of this, I'll sort of we'll be able to just talk interchangeably about the optical network, meaning the list of beam splitters and phase shifters, or the unitary transformation that's applied from that network by that network. Okay, because it's very easy to convert between one and the other. Okay, so this is already a big difference between the optics model and the standard qubit model, right? In the qubit model, just to describe, the entries, of our, first of all, the space of possible unitary transformations is vastly larger in the qubit case. Okay, just to specify any one of them takes, an exponential number of bits, exponential in the number of qubits. And as Stephen pointed out, almost just by a counting argument, almost every quantum circuit acting on qubits requires an exponential number of gates. Okay, that's not true at all here. Here, any quantum circuit that you like within this model can be implemented with just a polynomial number of gates, with order m squared of them.
But these aren't the most general unitaries you can have.
That's absolutely true. Yes. Right. So the reason why we get this reduction is that we're only considering a restricted set of unitaries, namely the linear optical ones. Okay. Yeah. Okay. Yeah.
The analog of m in the qubit case would be 2 to the n, right? Not n.
It depends what you mean, right? If you're talking about what is your physical resource, right, then the number of modes seems like a good analog of the number of qubits. Okay, so
Can you just say again what was the definition? What makes you special other than that you can just make it out of use?
What makes you special?
There's a theorem here. So some restricted set of the unitaries on the Hilbert space can be made out of order m squared of these things.
Yeah. Okay. These are what are called what I'll define to be the linear optical unitaries. Okay. These are okay. So I'll give you a definition, right? You might not, but you might not like it. So I could say it's equivalent to saying, it's the unitaries that you can implement without needing any interaction between the photons. Okay. So it's just treating the photons just as in the free field theory, okay, as identical non-interacting particles.
But it's more than just permuting them all.
Yes, it's more than permuting them, because you can do you can do a beam splitter, for example. So all right, so maybe it'll be clearer if I the key fact that we're going to exploit is that once you specify this m by m unitary that just acts on a single photon, that automatically induces a unitary acting on the larger Hilbert space involving n photons. Okay, so we get the bigger unitary for free from the smaller one, in some sense. And so what's going to happen is that U is going to give, which is our little m by little m unitary, is going to give rise via homomorphism to a big M by big M unitary, which I'll call phi of U. Okay, and another way to say it is that this is just going to be some very large representation of the unitary group. Okay, and so how do we do this? How do we get to this bigger unitary? So here's the amazing fact. So I'll show you there are several different ways to define this phi of U, but here's the one that will be sort of most instructive for us. Okay, so I'll just define the individual matrix elements of this phi of U. So let's say that we've got two basis states, S and T. Okay, so these are both lists of non-negative integers summing up to n. Okay, so we want to know what is the scattering amplitude, I guess, or what is the transition amplitude for getting from, the photons being in this configuration to the photons being in that configuration. Okay, that's just this thing here. Okay, and it turns out that formula for it is the following. So it turns out that to get each entry of this big unitary, we're going to take the permanent, remember the permanent from yesterday, of some matrix which is defined in terms of the smaller unitary. I'll explain shortly what this is, and then there's some normalizing factor here. Okay, so what is this UST? It's just it's simply the n by n matrix obtained from U by taking SI copies of U's ith row and T sub j copies of U's jth column for all I and j. Okay, so to clarify, so suppose we're in the special case where each SI is either 0 or 1. Okay, and by the way, let me give that a name. If there's either 0 or 1 photon in each mode, then let me call that a collision-free basis state. Okay, and the collision-free ones will be, it'll often just be very convenient to restrict our attention to those. Okay, these are the ones where we don't have any bunching of multiple photons in the same mode. Okay, so now if we're in if S and T are collision-free basis states, then this UST is simply an n by n submatrix of U, right? It's just you take the corresponding rows of U, n rows of U, the corresponding n columns, and you just look at what submatrix they form. Okay, if you've got multiple photons in the same mode, then you may have to take some repeated rows or repeated columns. So it's not literally a submatrix. Okay, but it's still sort of morally a submatrix. Okay, so there's you stare at this formula. There are several questions that one could ask about it. Yeah? Oh. Okay. One is, why is it true? Why is it the right formula? You could ask, is it really true that phi is a homomorphism? And you could ask, is it really true that phi of U is a unitary matrix? These are certainly not obvious, by just staring at the formula if you didn't know where it came from. Okay, so, make a long story short, the way to answer all three of these questions is to switch to this representing the photons in terms of these formal variables. Some of you might know these things as creation operators. Apparently, that's what they're called. So if you just, represent your state in terms of these creation operators, then, you can actually just quite easily derive this formula. And, I think I put that on the homework. If not, you can try it anyway. Okay. And so, it's actually not hard to give some intuition about where this permanent function is coming from here. Okay. The intuition is simply that, well, look, photons are, these photons are identical bosons, right? So let's say that you have n bosons, let's say in different modes, and we want to know the amplitude for them to transition to this other configuration. Okay, then quantum mechanics says we've got to sum over all possible paths that by which we can get from here to here. Okay, so in particular, we've got to sum over all n factorial possible ways of permuting these particles around, right? Because each one is going to lead to exactly the same final state. Okay, and so then we need to add an amplitude for each one of these things. And what are each of these amplitudes? Well, each of them is just going to be the product of like a transition amplitude for going from mode I to mode J, right? For each of these J's. But if you think about that, that just gives you, if you were to write out the n squared different transition amplitudes in a matrix, that would just exactly give you the permanent of that matrix. Okay, and to just build intuition further, the permanent would even arise if we were talking about classical particles. Okay, imagine that you had n balls and you threw each one into one of n bins, right? According to some, let's say each one according to its own probability distribution. Okay, and now suppose you wanted to know something like what is the probability that all n balls will land in different bins? Okay, that's again a permanent. Okay, right? Because again, you've got to sum over n factorial different products of probabilities, and so you write out the probabilities in an n by n matrix, then it's going to be the permanent of that matrix. Okay, in this case, it's a permanent of a matrix of probabilities, a non-negative matrix. Here, we're talking about the permanent of a matrix of amplitudes, so a complex matrix. Okay, that's a huge difference. That's that's going to matter for us. But that gives you some idea of why this permanent that we know and love in complexity theory would be showing up in the basic laws of the universe. It doesn't explain where this normalizing factor comes from. I mean, that comes from basically the creation operators have these little things in them, and you need that to ensure unitarity basically. But okay. So, so just to give a little bit of intuition, I should give like one famous example of a phenomenon that we can describe using this language. So there's this thing in quantum optics called the Hong-O-Mandel, or the Hom dip. Okay, what is this? It's the effect where you take two identical photons and in two different modes, and you send them, I think you draw it like this, you send them into an optical network with a single beam splitter. Okay, and this beam splitter should just be applying the 2x2 Hadamard matrix. So it just applies this matrix here. Okay, and then you measure these two output ports to find how many photons each one has. Okay, it should be the other way. Yeah, thanks. What? Okay, so yeah, I get those confused. Okay, so now what you find if this experiment is done perfectly is that with half probability, you find two photons in the first mode. Okay, with half probability, you find two photons in the second mode. Okay, but again, in the at least in the ideal case, you never find the two photons in different modes. Okay, and now this is this seems very mysterious. Why? Because the photons never actually interacted with each other. Right? As we said, these are non-interacting particles, and yet somehow their behavior has become correlated. Okay, so what is the explanation for this effect? Well, just like with everything else in quantum mechanics, the explanation is ultimately the magic of interference, the magic of minus signs. Okay, so let's see in particular what's going on. Well, we can calculate an amplitude for the photons to stay in the same configuration. In other words, they start out in the state 1, 1, and then what is what is the amplitude for them to remain in the 1-1 state? Okay, well that is simply going to be, by this formula here, the permanent of the Hadamard matrix. Okay, what is the permanent of the Hadamard matrix? Well, you've got one negative contribution here, and you've got one positive contribution here. They cancel each other out. Okay, to say it more intuitively, there are sort of two things the photons could have done, right? They could have, this one could have, gone this way, and this one could have gone this way, or this one could have gone this way, and this one this way. Okay, and each of those possibilities contributes an amplitude, but one of them is positive, one of them is negative, so they cancel out, and the result is that we never see that outcome. Okay, which means that we can only ever see the other outcomes. Okay, so so we can easily understand this just by looking at the permanent of this 2x2 matrix. By the way, just to, little advertisement. So just very recently, Adam Boland, who's here, and I wrote a paper sort of showing that in fact this Rec et al. Result can be improved. In fact, even just this Hadamard beam splitter is sufficient by itself to approximate any unitary transformation on any number of modes, at least any real orthogonal transformation, let's say, to whatever precision you want. And furthermore, the same thing is true for any fixed beam splitter, as long as it does something which is non-trivial, right? Something other than just permuting the modes around or adding phases to them. Yeah.
Do you then still have this whole
Yeah, it's the same thing, order m squared. Yeah, with some log of 1 over epsilon or something that comes from the Solovay-Kitaev theorem. Yeah. Yeah, if you want an approximation to within epsilon of your target unitary. Okay. So okay. So okay, but now we're going to be interested in case of a lot more photons, a lot more modes, and ultimately what we're interested in is going to be what is the computational complexity of simulating this sort of setup. Okay, so what can we say about the computational complexity of simulating, a quantum optical network? So I'm going to start with sort of some really basic observations about this, and then we'll sort of build up toward, toward more interesting things, I guess. Okay, so. Okay, so the first sort of doofus observation is that we could, in principle, take any quantum computation that we wanted, Shor's algorithm, whatever, any quantum computation on n qubits, and we could simulate it using an optical network, with, in fact, even just with one photon. We would merely need, a hell of a lot of modes. Okay, one mode for every basis state in our Hilbert space, right? So. Particular, we would to simulate n qubits, we would need 2 to the n modes, okay, to do it this way. Okay, and this, we are going to consider to be an exponentially exploding resource. Okay, so this is not, a reasonable, or an interesting way to simulate a quantum computation, because in real life, we don't have 2 to the n modes, right? You try to sort of, in fact, the holographic principle would rule out that you could have that many modes in a, in a small enough space without creating a black hole. Okay, so no, it's both, because if you had yeah, okay. So okay, so what this tells us is that if we're to have any hope of getting a speed up, then we're going to need to consider lots of photons, right? Okay. Second observation. Let's see, what order do I do? Okay. Okay. Whatever else, we're certainly not going to be able to do more with this optical setup than we could do with a standard qubit-based quantum computer. Okay, or in other words, this sort of linear optical network can certainly be simulated in BQP, in quantum polynomial time, in the usual sense. Why is that? Well, because you can use the algorithms that Stephen talked about in his talks for simulation of quantum systems. In this case, in fact, a particularly simple quantum system, just a system of free, non-interacting bosons. Okay, and we know from the work that goes back all the way back to Feynman in the 80s, and Seth Lloyd and people like that yes, you can simulate, a system of bosons, of n bosons, let's say, in m modes with just a standard quantum computer. Okay, and this, the way you do the simulation is that, like, for each mode, let's say you would have log of n qubits, let's say, right, that just records in binary notation how many photons, do you have in that mode. Okay, so you'd have a bunch of registers, each of them with log n qubits, and then you would just need to show how do you simulate a beam splitter or a phase shifter in this way, right? So a phase shifter will act on just one of these registers, and it will just apply, it'll basically just apply e to the I phi to, times the number of photons in that mode. Okay, so that's certainly easy to simulate. And a beam splitter will act on two of these registers, and that's a little bit more complicated. Okay, but in any case, it's merely some n by n unitary transformation, and we can describe it explicitly. And then the Solovay-Kitaev theorem tells us that we can apply that using only a polynomial number of qubit-based gates. Okay. In fact, I just learned from Steve yesterday that there's even a faster way to do this simulation using what's called the quantum Schur transform. Okay, but this is one way to do it. Okay, so that's observation 2. So you might ask, is this just is linear optics just giving us yet another redefinition of BQP? Okay, but my third observation will say probably not. I can't say with certainty, but I claim, at a physics level of rigor, that this linear optics model is probably not universal for quantum computation, or even, for that matter, for classical computation. Okay, and why do I say that? Well, just because you can count, as I said before, you can just count the number of unitaries that you have available to you in both cases. And, in the linear optics case, our entire space of unitaries, is parameterized by just only m squared parameters, right? M squared real numbers. Okay, so, it's true that these at little m by m unitaries that we can choose then get lifted by homomorphism, right, to these, gigantic unitaries acting on our full exponentially large Hilbert space. Okay, but in some sense, we're only ever applying unitaries in this tiny subgroup of the full unitary group, on our full Hilbert space. Okay, so that, just comparing the dimensions of the two, unitary groups immediately rules out that you could ever have a direct sort of gate-by-gate simulation of an arbitrary quantum circuit using linear optics. Okay, you don't even have, in fact, linear optical versions of the controlled NOT gate or the Toffoli gate or the basic building blocks like that. No, I can't rule out the possibility that there's some much more bizarre simulation. Okay, and it would be interesting to give some evidence against that. But okay, because you could imagine that there would be some weird reduction where for every polynomial size quantum circuit or something, right, there would be some way to just get you wouldn't be, applying a homomorphism, right? You wouldn't be doing a direct mapping of unitaries, but you would do something else. You would transform it into some totally different looking thing in the optics model, but that would give you the answer to the same computational problem.
It's not universal for arbitrary.
Oh, that's right. But I can't show that every decision problem that's in BQP is not also solvable with linear optics, right? That would require solving P versus NP, scale problems in order to prove such a thing. Okay, so, but yeah. Okay.
Could you just add another gate or something?
Oh, okay. So in fact, that brings me to point number 4. Thanks. So, okay, you can certainly add another gate. So you can add what's called nonlinear optics. Okay, you can add optical nonlinearities, and that will very quickly give you all of BQP. Maybe not so surprisingly. Okay, but in fact, there's also a much more interesting and surprising thing that's known, this was discovered by Knill, Laflamme, and Milburn, or KLM, in 2001. Okay, and what they discovered is that if you just take pure linear optics and you just add one more resource to it, which is called adaptive measurements, then that gives you all of BQP. And that suffices to build a universal quantum computer. What does adaptive measurements mean? Okay, it just means that at some intermediate point, in your optical network, you're allowed to measure some mode, see how many in the Fock basis, see how many photons there are in that mode, and then depending on what answer you get, you can change the beam splitters that you apply to the other modes. Okay, so that's what's called adaptive or feed forward measurements. Yeah, Dorit.
What's your best simulation of linear optics?
You mean without the adaptive measurements? Okay, so actually it depends, what answer you're trying to get, right? But so I'll mention that there are some non-trivial simulation algorithms due to Leonid Gurvitz, okay? But if you want like a full simulation of the full output distribution, then they're going to take time, that's at least like 2 to the n. It's certainly going to be exponential in the number of photons. Okay, yeah.
Could you also find a way to duplicate BQP by allowing more complex particle physics interactions?
Absolutely, yeah. So that's exactly what these nonlinearities are. Okay, as soon as the photons are able to interact with each other, then you very quickly get up to universality. Okay, now from a practical point of view, problem with that is that photons don't like to interact with each other, or so I'm told. Okay, they tend to just kind of fly past each other at the speed of light. So. Yeah. So right. So what people have thought about in practice to implement these nonlinearities is to use like an atom as the intermediary to get the photons to talk to each other, right? And and that's you could in principle do that. One obvious problem with it is that you're going to introduce a hell of a lot of decoherence if you try to do that, right? A wonderful thing about photons from the applied point of view is that they have fantastic coherence times, right? If they were just flying through the vacuum, right? There are photons of the cosmic microwave background that are hitting us right now that some of which may have maintained their quantum coherence for billions of years, right? Of course they're not staying still. If you want your photon to also be confined, then and maintain its coherence, then that's harder. Okay. But yeah, so this but the difficulty of getting the pairs of photons to talk to each other is why the KLM discovery was so interesting and exciting. Okay, what they showed is that even without any interaction between the pairs of photons, you could still do universal quantum computation as long as you have these feed-forward measurements. Okay, as long as you can just measure and then adapt your optical gates based on what you see. In effect, these adaptive measurements let you create interactions. They let you simulate the effect of interactions between the photons, even when you didn't have them before. Okay, and this is going to be, important for us going forward. Okay, this result. Okay. All right, so let's move forward observing things. Okay, so a fifth instructive observation is suppose that we took exactly the same setup as this, except instead of bosons, we took fermions. Okay, so we had identical non-interacting fermions. Okay, then it is known that such a system could be simulated completely in classical polynomial time. Okay, now why is that? Well, you have to give a simulation algorithm, and it takes a little bit of cleverness. But the key observation behind the simulation algorithm is this, that with fermions, the transition amplitudes are given not by the permanent of an n by n matrix, but can anyone guess by what? Oh, right. Yep. So this permanent determinant dichotomy that is so central to complexity theory turns out to be mirrored as well in God's own laws. Okay. So the reason why you get the determinant, yeah.
Is this with adaptive measurements or?
Oh no. I'm sorry. In fact, you can even handle adaptive measurements. Yeah, the simulation will still work even if you have adaptive measurements. That's a good question. Yep. Okay. Okay. The reason why you get the determinant with fermions is that you take two identical fermions and you swap them. Then by definition you pick up a -1 phase, right? And so then you're going to be summing over all n factorial permutations of your n particles. But for each one you're going to have a factor which is -1 to the number of swaps. Okay, that of course gives you exactly the determinant of an n by n matrix. Suddenly, I just recently I read this new book by Steven Weinberg about non-relativistic quantum mechanics, and so one thing he gets up to talking about bosons and fermions, and he says for fermion, if you have n identical fermions, their transition amplitude is given by what's called the Slater determinant of an n by n matrix. And he says he remarks that for bosons it is also a determinant except without minus signs. Okay, so this determinant without minus signs, right, will be of enormous interest to us because it really is very, very different than the one with minus signs. And what we're starting to see here is that this difference will also have very big implications for the computational complexity. Okay, simulating the dynamics of non-interacting fermions is easy for a classical computer, basically because the determinant is in P. You still have exponentially many different determinants here, and so you still need some cleverness to get the simulation algorithm. But one can do it. I'll be happy to explain it offline if anyone's interested. Okay, yeah.
So in point number 4, how many gates do you need for?
So it's a polynomial. It's basically in fact in the KLM simulation, it's really just like a constant blow up. I think, in the size of the circuit, right? So like with a constant number of optical gates, you can, plus the adaptive measurements, you can simulate a single qubit-based gate. Okay, so the size of your optical circuit will be only a constant factor larger than the size of your original circuit. Okay. So, with bosons, you get the permanent, and and that makes things a lot harder. And I think there's sort of no way to avoid talking about this the permanent and determinant as the reason why bosons are harder than fermions here. So there was a paper not long ago saying, well, look, there was this paper by Aaronson and Arkhipov that gave all these complicated, like incomprehensible complexity reasons why why this linear optic should be hard to simulate. But we're going to eliminate all that, and we're going to give a simple physics, a physical reason why it's hard. And then they say the reason why it's hard is that your Hilbert space is exponentially large. And of course, an immediate problem with that is that would also suggest that fermion sampling would be hard, but it isn't. So then, I pointed this out to them. They revised the paper to say, well, this boson sampling is hard because it's an exponentially large Hilbert space, and also because it involves this permanent, which is which is apparently computer scientists think is a hard function. So, okay. By the way, I should point out an irony here, which is that many people might know that in condensed matter physics, if you're trying to find ground states using quantum Monte Carlo, then with fermions it tends to be very hard to do because of what's called the sign problem. Okay. Whereas with bosons, it's much easier. Okay, and here, ironically, the situation is reversed. Okay, so the best thing I can say about that is that sometimes minus signs are your friends, sometimes they're your enemy. Okay, quantum Monte Carlo, they're your enemy. But when we're talking about simulating non-interacting particles, then they become your friend. Why are they your friend here? Because they mean that you only have to calculate determinants instead of permanents. Okay, so so this brings us to observation number 6, and this is something that we already discussed yesterday. It is known, has been known since the 1970s, that computing the permanent of an n by n matrix is a sharp p-complete problem. Okay, it is way up in this hierarchy of complexity theory. So in fact we might as soon as we realize that, we might be tempted to leap to conclusions and say, well, gosh, the permanent is sharp p-complete. Linear optics involves permanent somehow. Therefore, linear optics is exponentially hard to simulate. What more proof do you need? Okay. Unfortunately, that is not a good argument, and I'm going to explain to you why why more work is needed. Okay. So actually, the first people to, at least in print, put these facts together that bosons involve the permanent, and the permanent is sharp p-complete. Ergo, bosons somehow involve sharp p-completeness. Were actually, I believe, at Hebrew University, Troyansky and Tishby in 1996. Okay, so they pointed out this connection, but then they also tried to go further and say, well, so what would happen? Could you actually use this connection to solve a sharp p complete problem using an optical quantum computer, right? Would that be possible or not to do? And so they thought about that a little, and they realized that there was a problem. Okay, so to explain the problem, all right. So first, we need to say a little bit more about the complexity of the permanent. Okay, so the first thing, yeah. Yeah.
Sharp p gives counts something, right?
Yes.
It's permanent, it's like computing something, but what is it counting?
Well, if you had a matrix of zeros and ones, then you're counting the number of matchings in a bipartite graph, as we discussed yesterday, right? And for more, if you had a matrix, say, of complex numbers, then you're not obviously counting anything. But so in that case, actually. So my bad. It wouldn't. The problem might not literally be in sharp p, but so I should say that it's then sharp p hard. Okay. The answer is not necessarily a non-negative integer, but in any case, you can use it to solve a sharp p problem. Okay. Thanks. Yeah.
So the unitary we are calculating the permanent has a special structure which is given by the construction. function, right?
Yeah.
That limits the scope of the unitary we are calculating.
So yeah, that's something you might worry about. I'll show that you can actually get around that problem, but then another problem shows up. Okay? So, all right, so the first observation that we can make is that, amplitudes in quantum mechanics are not directly observable, right? In general, just because a hard problem occurs in a particular formal description of some physical system, right, you can never conclude on that basis alone that simulating that physical system is hard. Okay, you always have to go further and ask the question, well, can I actually measure the system and actually get out an answer to a hard problem, right? That's what we care about. Does the answer to a hard problem occur in reality, not in a particular formalism for describing reality? Okay, so and so then we'll notice in fact amplitudes are not directly measurable. We use them to calculate the probability of seeing this versus that. Okay, so even in the best case, we could only ever hope to get an approximation to the permanent, right? And so then we could ask, well, is that still a hard problem? Okay, and this turns out to be an interesting story in itself. Okay, so it turns out that if you have a matrix of non-negative entries only, then there is computing the permanent of such a matrix exactly is still a sharp P-complete problem. But there is a remarkable algorithm from the 90s due to Jerem, Sinclair, and Vigoda that approximates such a permanent to whatever multiplicative precision you want. So let's say to plus or minus 2% error, plus or minus 1% error, whatever, in randomized polynomial time. Okay.
The matching one is non-negative, right?
Yes, it is. So in particular, this algorithm approximately counts the number of matchings in a bipartite graph.
I mean, the number is an integer, so if you can count an integer to a small.
No. Okay. So I should be clearer. The amount of time needed by the algorithm is polynomial both in n and in 1 over epsilon, where epsilon's your error. So if you want to, get this exponentially large integer to within plus or minus 1, then, this is going to blow up in your face. All right? Good. So, yeah, epsilon is your relative error. Thanks. Yep. So, so this was a dramatic application of what's called the Markov chain Monte Carlo method. Okay, basically what you do is you take a random walk on the space of all possible matchings of your bipartite graph, and then you prove that such a walk mixes, approximately after only a polynomial number of steps. And then you observe that there is a connection between sampling and counting, where if you can approximately sample a random matching, then you can use that to approximately count the number of matchings. Okay, which again takes some thinking about. Okay, but and I should say that this algorithm, the proven bound on its runtime, is something like n to the 7, or it's pretty bad. But my guess would be that the actual runtime is actually much better than the theoretical guarantee. Okay, so but on the other hand, non-negative matrices. All right, so that sounds bad for the prospect of solving a hard problem this way. Okay, but hey, we're not dealing with non-negative matrices, right? We're quantum mechanics, woo, right? We get matrices of complex numbers. Okay, and it turns out that if you've got an n by n matrix of complex numbers, then even approximating the permanent of A, or in fact, even let's say the squared absolute value of the permanent of A to small relative error is already a sharp p-hard problem. Okay, why is that? let me try to give you some intuition for it. Okay. So the basic idea here is to give a reduction. This is what we know how to do in computer science, right? And we're going to argue that for arbitrary matrices, if you could even approximate the permanent, efficiently, then in fact that would allow you to compute the permanent exactly, which we already know is sharply hard. Okay. So how does that work? So let's say you've got some n by n matrix A. Okay. So then let me define A sub x to be A plus this matrix that just has an x in the top left entry and a 0 everywhere else. Okay. And let me also define B to be the bottom n minus 1 by n minus 1 submatrix of A. Okay, so then I'll observe the following. What is the permanent of A sub x? Anyone? Well, it's just going to be the permanent of A plus x times the permanent of B. Right? Right? You can just, stare at that and see that that's true. Okay? So, but this is very useful because what this means is suppose that, I know how to approximate the permanent of A sub x to small multiplicative error. Okay, now I can just keep twiddling x. I can keep changing x, and just keep approximating this thing over and over again. If I can approximate something to within relative error, then in particular I can decide whether it's positive or negative. Okay, so I can figure out for which x does this thing cross the origin. Okay, so in other words, I can solve the equation 0 equals permanent of A plus x times permanent of B. Once I know that, then I know that the permanent of A is just minus x times the permanent of B. So what have I done? I've reduced the computation of an n by n permanent to the computation of an n minus 1 by n minus 1 permanent. Okay, because I know x. Also, I picked x. Okay, so now I just recurse. Now I just run the same algorithm in order to get the permanent of B, and to reduce that to the computation of to the approximation of the permanent of an n minus 2 by n minus 2 matrix. Okay, and so forth. Okay, and until I get down to a 1 by 1 matrix, and then I know it's permanent. Okay, so okay, and you'll notice that that we really needed here that we could adjust x to be either positive or negative. This would not have worked for non-negative matrices. Okay, so that sounds like good news. Approximating the permanent is already sharply hard. Okay, so now what happens if we try to use that to set up a linear optical experiment that will give us an estimate of the permanent of a matrix of our choice? Okay, well, so let's say that we've got some n by n matrix A. And we want to know its permanent, approximately. Okay, well, the first thing we'd have to do, as was already pointed out by someone, is that we would have to somehow embed A, let's say, as a submatrix of a unitary matrix, right? Because we can only apply unitaries in quantum mechanics. Okay, well, of course, if A has entries that are, more than 1 in absolute value, then, it's never going to show up as a submatrix of a unitary. But that's not such a problem, because we can always just rescale A, right? And so here's here's something that I put on the homework, and that, you can enjoy proving or not enjoy, whatever. So for any n by n matrix A, there exists a 2n by 2n unitary matrix U, which contains some rescaling of A as its topmost n by n submatrix. Okay, and moreover, you can very easily find that U if you're given A. Okay. This is a linear algebra exercise, right? Show how to embed any matrix as a submatrix of a unitary matrix, which is twice as large. Okay? And what will this epsilon be? This epsilon will basically be just 1 over the norm of A. The norm means just the largest singular value of A. Okay? So, all right, so you can certainly create this kind of unitary, this kind of 2n by 2n unitary. Okay, and let's say that we then, so we set m equal to 2n. We set up an optical network with n photons and with 2n modes. Okay, and we start out with this standard initial state. So our first n modes are occupied. And we then apply that unitary, and we check for what is the probability that we'll return to the same state that we started with. Okay, the probability will be this, and you can calculate that using the formula for these amplitudes that I gave before. And this is just going to be epsilon to the 2n times absolute square of the permanent of A. Okay, so you can. So what this is saying is you can indeed, construct an experiment, for any given n by n matrix A will produce a certain observed outcome with probability that depends on the permanent of A. Okay, you can do that. Okay, so great. It sounds like let's go out and build this thing, and we'll solve short p problems with a quantum computer, right? And that's even with a very simple one, okay, that's even better than NP complete problems, right? This is even way beyond even D-Wave's wildest dreams, right? So why not do it, right? What's the fly in the ointment? The problem, is this, that in general this quantity here, this probability will be exponentially small. Right, I pick some arbitrary matrix. Right, usually to embed it into a unitary, I got to multiply it by a small epsilon. And that's gonna and this thing is this quantity will be exponentially small, which means that yes, I could estimate it. Eventually, if I repeat my experiment enough times. But in order to get any non-trivial estimate of this thing, and therefore of my permanent, I'm going to have to repeat the experiment an exponential number of times. Until I can get this I to show up even once. Okay, and so if I have to repeat exponentially many times, then I'm not getting any advantage over just doing the thing with a classical computer. Okay, so so that seems like a real downer. Okay, but now you might still hope to save the idea. You might say, look, how about just we just try to do this for those special matrices A that can, naturally arise as a submatrix of a unitary matrix, right? So forget about arbitrary matrices. Just take, those things, that are just naturally, submatrices of unitary matrices. And let's say, look, we're not going to even try to detect, to estimate the permanent if it's exponentially small, right? That's hopeless. Okay, but at least if the permanent of this submatrix happens to be really large, happens to be close to 1, let's say, then our quantum experiment can detect that. So, can your classical algorithm do that? Well, unfortunately, it turns out that a classical algorithm can do that. Okay, so this then brings us to one of the beautiful results in this area due to Leonid Gurvitz. Okay, and so what Gurvitz gave is he gave an algorithm that approximates the permanent of any matrix, doesn't have to be non-negative here, to within a small additive error epsilon, in time that's, in fact, a small polynomial in n and in 1 over epsilon, just quadratic, assuming that A has bounded spectral norm. Okay? In fact, Gervitz's algorithm is so simple that I can just fit it on just a small part of this board, I think. So B is you use something called the Glynn formula, which also gives the fastest known algorithm for exactly computing the permanent. Okay, this is a really cool formula. So it turns out that for any matrix A, you can write the permanent of A as the expectation over all x1 up to xn, that are 1 or minus 1, of the product of those xi's times product from I equals 1 to n of A I1 x1 up to okay, so here's a remarkable formula for the permanent, which was known since the 1960s. And actually, I also have on the homework to prove that this formula is correct. Okay, it's really not that hard. You stare at it, you observe that a bunch of terms cancel, and that the terms that are left over are the permanent. Okay, so so this has some remarkable features. One of them is that it gives you a non-trivial algorithm for exactly computing the permanent, because now instead of summing over n factorial terms, which you would have to, which would be the naive approach, here you merely have to sum over 2 to the n terms, okay, which is an improvement, right? And each one takes n squared time to evaluate, so you get an algorithm with this complexity. In fact, I'll leave this as a puzzle for you, but by being a little bit more careful about how you evaluate this expectation, you can even get the time down to 2 to the n times n. Okay, by being more careful about how you iterate over these xi's. Okay, now this for 60 years has been the fastest known algorithm for the permanent, in general. Okay, which if indeed it's sharp P complete, then it wouldn't be surprising that you need exponential time. But we don't even know how to beat this. Okay, now what Gervitz observed is that suppose you just want to approximate the permanent. Okay, but now suppose that A has bounded norm, then it turns out one can prove then using like arithmetic geometric mean inequality that that this thing inside the expectation is always at most 1 in absolute value for a bounded norm matrix. So once you know that, then you very quickly get your approximation algorithm for the permanent. What is it? Just pick a bunch of x strings at random. Okay, evaluate this thing in the middle for each one and take the average. Okay, that's the algorithm, right? And okay, so but as simple as it is, what this algorithm says is that any time the linear optical experiment would detect that the permanent of your submatrix is large, Gervitz's algorithm will also detect it. Okay, so in this way, you're once again not getting any actual speed up for a computational problem using this approach. You're certainly not solving a sharp P complete problem. Okay, so once again, bummer, right? Okay, so now what did So what did we do? What we basically said is, well, how about if you just give up on the goal of calculating the permanent, or for that matter, of doing anything else useful? Just consider the problem of simulating this experiment itself. Okay, maybe at least that is hard. Okay, and so this motivates us to define a problem which I'll call Boson sampling. Here, you're given this m by m mode. Your input is this m by m mode mixing unitary U. Okay, so here, we'll let D sub u be just the probability distribution over experimental outcomes, which is sampled by your linear optical machine. What is the problem? The problem is to output a sample from that same distribution. Okay, so certainly you would need a randomized algorithm to have any hope of doing that. But question is, can you do this by an efficient classical randomized algorithm? That's now a question that one could ask. Okay, and then once you ask that, then there's actually a quite a really easy theorem that one can prove. The theorem is suppose boson sampling had a polynomial time classical randomized algorithm. Then this would have the consequence that p to the sharp p would equal bpp to the np. Okay, and that in turn would be bad. Okay, so do I have 2 minutes or? Huh? Yeah, I'm only talking right now about exact sampling. Okay, so in fact, I've already told you, essentially everything that is needed to prove this. Okay, so the observations are this. Let p be this probability, the probability of returning to your starting state. Okay, which in turn is like this scaled permanent. Okay, then we saw that even approximating this quantity is already a sharp p complete problem. Yeah.
Yeah, well, I'm wondering, how do you convince someone that you really sample from you?
So we're going to get to that in the next lecture. Okay, good question. Okay, we're going to discuss that, and that's definitely an issue. Okay, but let's just suppose that you had this this simulation algorithm. Okay, then what would its consequences be? Okay, so all right, so we saw that even approximating this probability is already a sharp p complete problem. I didn't prove that for the absolute square of the permanent, but that's not hard to do either by just a simple modification to the reduction that I gave. Okay, so we're just putting together two facts, really. The first is that approximating p is already sharp p hard. Observation 2 is that if we had this hypothesized classical simulation algorithm, then we could approximate p in a different complexity class, namely in BPP to the NP. Okay, now why is that? Well, this also, again follows from sort of a known technique in classical complexity theory, which I don't have time to get into, but the technique is called approximate counting. Okay, and basically what this says is that what approximate counting lets you do is it lets you approximate any sharp p quantity, so any sum of a bunch of non-negative terms in BPP with an NP oracle. Okay, and how do you do it? Because you use your NP oracle. That can tell you whether a non-negative term exists, right? So that can at least at the least that can tell you whether your sum is 0 or non-zero. Okay, but that's a pretty crappy approximation, right? You'd like to do better. So what do? Well, now you use your BPP power to just keep picking random hash functions. Okay, and you do like Rumpelstiltskin. You say, okay, fine, you tell me that there's, a 1 in this sum, but is there a 1, whose index also hashes to the following value? There is? Okay. How about whose index also, satisfies the following additional random constraints that I'll pile on? And you keep piling on more and more random constraints until suddenly there's no more 1s in your sum, and now your sum is just pure zeros. Okay, and then you look at how many random constraints that you have to add to get to that point. Okay, and that number of constraints you had to add gives you a pretty good, multiplicative approximation of how many 1s there were to begin with. Okay, that's the basic idea. This was, from a technique from the 80s. Okay, so, in particular, suppose that M was our classical simulation algorithm, then we would just have to look at, for what fraction of random strings R that could be fed to M as input will M output, this state I. Okay, right, and that will equal by assumption, the P that we care about. Okay, so, again, we're using the fact that, about classical randomized algorithms that I mentioned yesterday, that anytime you have such an algorithm, you can pull the randomness out of it. You can view it as just a deterministic algorithm that takes a random string as an additional input. Okay, so now all we have to do is put these two facts together and say, suppose you had this fast classical algorithm, then you'd be taking a sharp P quantity and you could estimate it in BPP to the NP. So in particular, you could handle lots of calls to a sharp P oracle, just one after the other. That would let you do P to the sharp P in BPP to the NP. Okay, well, who cares about that? Well, I told you all this random stuff yesterday, right? I told you that the polynomial hierarchy is contained in P to the sharp P. Okay, now we know that would be in BPP to the NP. I also told you that BPP is contained in the polynomial hierarchy. In particular, BPP is contained in NP to the NP. And the proof of that is what's called a relativizing proof, which means that if you've got an NP oracle, then everything goes through just the same. You get BPP, BPP to the NP is an NP to the NP to the NP. So bottom line, we now have that pH is an NP to the NP to the NP. Therefore, the polynomial hierarchy collapses to the third level. That's where we've got to. So it's late. Thanks.